Okay, chapter 3, last example, example 7. A piston cylinder device contains 50 kg of water at 250 kilopascal and 25 degrees Celsius. The cross-sectional area of the piston, okay, cross-sectional area of piston is 0.1 meter square. Now heat is transferred to the water, causing part of it to evaporate and expand. When the volume reaches 0.0 meter cube, the piston reaches a linear spring whose spring constant is 100 kilonewton per meter. More heat is transferred to the water until the piston rises 20 centimeter more. Determine A, the final pressure and temperature, B, the work done during this process. Also shows the process on a PV diagram. Okay, now we have water on this we have water on this piston cylinder arrangement, and okay, I think it's better to use the PDF to discuss the solution. Okay. Okay, these are the initial parameters. Mass of the water is 50 kg, and P1 or initial pressure is equal to 250 kilopascal, temperature 25 degrees centigrade, and piston area 0.1 meter square. Okay, and when the piston touches the spring, volume of the water is 0.2 meter cube, and the stiffness of spring K is equal to 100 kilonewton per meter square. So in this process we have three stages: stage 1, the initial stage, and the stage 2 when the piston touches the spring, and stage 3 after the spring compressed. So we have three stages on this arrangement. For stage 1 we have P, T, and I think M. Okay, we have these three properties for stage 1. For stage 2 we have volume, V2 is equal to 0.2 meter square. Then for stage 3 we have the displacement, or the distance that the piston moved from stage 2 to stage 3. Now let's find the pressure first. Okay, to calculate the pressure, first let me show you in this arrangement. From stage 1 to stage 2 it's a constant pressure process because there's no change on this piston. So from stage 1 up to stage 2 it's a constant pressure process. From stage 2 up to 3, due to this spring there is additional pressure onto the piston. So due to that additional pressure there is additional pressure in the water. So to calculate the final pressure, P3 is equal to P2 plus P spring, the additional pressure due to this spring. So pressure 1 and pressure 2 are the same because it's a constant pressure process. So pressure 3 is equal to pressure 2 plus pressure due to the spring, and pressure of spring is equal to force of spring over area, and force of spring is equal to stiffness times change in X. Okay, and so we have the value of K and change in X. Change in X is equal to 20 centimeter. The additional displacement, or the additional distance the piston moved upward direction, and it's equivalent to 0.2 meter. So spring force is equal to 1000 times 0.2, it's around 20 kilonewton, and spring pressure equal to force of spring over area, and these are the values. So spring pressure is equal to 200 kilonewton per meter square, which means 200 kilopascal. Then the final pressure P3 is equal to P2 plus the additional spring force. Then the final pressure is equal to 450 kilopascal. Okay, now let's determine the final temperature. First, before we determine the final temperature, first let's determine the state of the final stage, because the pure substance is water and the final pressure is determined from table. So to determine the final temperature, first we have to determine the final stage to use the water table. To find out the state, first we have to find out the final specific volume, because in the final stage, stage 3, we have only P3 pressure. So to determine the state, we need two properties. Then we have to calculate the volume, and V3 is equal to V2, it's given, plus change in volume, the additional volume that the piston move upward to compress the spring, and the additional volume is equal to the height times area, because we have the height 20 centimeter or 0.2 meter, and area, piston area, 0.1 meter square, and the additional volume is equal to 0.02 meter cube. So V3 is equal to V2 plus change the additional volume. V2 is 0.2 meter cube, and the additional volume is 0.02. Then V3 is equal to 0.22 meter cube. But to use steam table, we have to convert this meter cube, this volume, into a specific volume, and specific volume 3 is equal to V3 over total mass, and total mass is given. So specific volume at stage 3 is equal to 0.0044 meter cube per kilogram. Now, using the final pressure 400 kilopascal and the final specific volume 0.04, we can determine the state. So from steam table, at P is equal to 400 kilopascal, let's read the value of Vf and Vg. So from steam table, at P is equal to 400 kilopascal, at P is equal to 450 kilopascal, Vf is equal to 0.00108, and Vg is equal to 0.41392. Okay, 0.001088 Vf and Vg 0.41392, and our V3 is equal to 0.0044 meter cube. It's between Vf and Vg. So if given specific volume is between Vf and Vg, the state is mixture. So now we have the three properties: the final pressure, the final specific volume, and the state mixture. So if the state is mixture, the final temperature is the final temperature is at P is equal to 400 kilopascal Tsat. So from mixture table, at P is equal to 450 kilopascal, Tsat is equal to 147.90 degrees Celsius. So this is a final temperature of this piston cylinder arrangement, and T3 is equal to 147.9 degrees centigrade, because the state is mixture. Now B, the work done during this process. The work done during this process has two stages. The first one is when the piston moves from the initial position to the spring, and the second work is after the piston touch the spring and move to the final position. So work done 1, 2, and work done 2, 3. We have 2 workers. So let's draw this process on a PV diagram. From stage 1 up to stage 2, it's a constant pressure process. Then the diagram will be on a PV diagram, the process will be a horizontal line from stage 1 up to stage 2. After from stage 2 up to stage 3, there is a linear spring on the top of the piston. So we have upward linear line because the spring is a linear spring. So from stage 2 up to stage 3, it's a linear upward direction. Then the work done during this process is area under this process curve from stage 1 to up to 3. Now area 1 is equal to V3 minus V1 times P1. Okay, so area 1 is equal to P1 times V3 minus P1. And area 2, so to before that we have to determine V1. To determine the value of V1, first let's find out the state at stage 1. So to determine the stage at stage 1, we have 2 properties, pressure and temperature. Using pressure and temperature, using graphical method, we can determine just the phase, and the initial state is compressed liquid. Using this, at t is equal to 25, p sat is equal to it's around 3.16, but the given pressure is above p sat, so the state is compressed liquid. Then to determine V1, first let's go to compressed liquid table. Okay, separated table, compressed liquid table, and the compressed liquid water table starts from P is equal to 5 megapascal, but our pressure is around 250 kilopascal, so it's difficult to use the compressed liquid table. So we use the mixture table at T is equal to 25. Read the value of VF 0.001003 because there is no table for compressed liquid at a given properties. Then from compressed liquid from mixture table can determine the given the initial specific volume. So V1 at T1 is equal to 25, VF 0.00103 meter cube per kilogram. Then V1 is equal to mass times specific volume, and it's around 0.05015 meter cube. Now we can calculate area 1. All the properties are determined, and area 2 is equal to 1 over 2. Let me use area 2 is equal to the difference between P3 minus P1 times the difference between V3 minus V2. Okay, this times this one over 2. So P3 minus P1 times V3 minus V2 over 2. Then we have all the values. Then we can calculate V2. Then the total work done during this process is equal to the sum of these two different areas, area 1 and area 2. Then we can obtain the value of the total work done. Now let's plot the process on PV diagram. On a PV diagram. Okay. On PV diagram, first we have this saturation line, saturated liquid, critical point, and saturated vapor line. At stage 1, the phase is compressed liquid, so the process starts around here in the compressed liquid region. Then from stage 1 up to stage 2, it's a constant pressure process. So we have a horizontal line. Then from stage 2 up to stage 3, there is a linear spring, so the pressure will increase. So we have a linear increasing line. But the final stage is still in a mixture state, so we stop here. Okay, if it's superheated, maybe we can move in this direction to superheated region, but the stage is a mixture, so we stop here. Then this will be the process on a PV diagram with the saturation line, and this is a constant temperature line for T1. T1 is 25 degrees centigrade, and this is a constant temperature line for T final, T3. It's around it's around 147.9 degrees centigrade final temperature. Okay, then this will be the end of example